So welcome back to the final session of the day. What we have done so far is we looked at an overview of GCC and then we have taken an external view of GCC by looking at the input program and the output program, or rather the dumps of the program at intermediate stages. So this was an external view of the generated compiler. Now we want to take an external view of the build process of the generator itself, and on the third day we'll take an external view of the specifications, the compiler specifications. So let's start looking at the configuration and building. What are the issues that are required when we say we want to build GCC, we want to configure GCC. So here is an outline. We'll look at how the GCC code is organized. We'll look at what are the steps that are required for configuring GCC. We're going to spend most of the time on first and second item. We'll spend a bit of time on how do we register new machine descriptions in GCC, how do we retarget GCC for new machine descriptions. We're still not talking about how do we write a new machine description. That's something that we will discuss on day 3. But assuming that we've been given a machine description, assuming that there's an existing machine description in our repository, how do we create a compiler for that particular machine and for our chosen input language? That's something that we will see today. There are 2 additional topics: building across compiler and testing GCC. It mostly consists of a lot of information, and a lecture tends to get very boring there. I have just included the material in the slides and you can go through them. We will not have lectures. One of the biggest tightrope walk that we had to do while building this material was to emphasize concepts and to separate concepts from information. We collect a lot of information, but information being given in form of a formal lecture tends to get very boring. So we've been trying to build concepts wherever possible and we're leaving information to the documents that you can read. This is what we will do. In configuration and building, of course, there are lots of pieces of information that we need to know, but there are lots of interesting concepts also that we will be talking about. So let's first look at how the GCC code is organized. Logical parts of a GCC are the build and configuration files, the front end plus the generic code plus the generator code. So there is a language dependent part, which is the front end. There is a language and target independent part, which is the generic code, and there is a target dependent part, which is the generator code and machine descriptions. Then we also need some emulation libraries. For example, there is a library called libgcc. Supposing your machine doesn't have a multiplication operation, but input programs have multiplication anyway. So GCC has identified many such operations which ought to be there on the machine. In case they're not there on the machine, not there in the machine description, GCC picks up a library function in order to carry out that task. Obviously, this library function will have to be compiled for our chosen target. libgcc is an example. Then there are also language libraries. There are support software, for example, garbage collector. Front-end code exists in the source directory, and we're going to use this convention. Our source directory is going to be denoted by a shell variable $source_d. It's not source because source is a built-in shell variable in Linux, so source_d. And so this is where we will assume that we have untarred the GCC source. That's the path to the directory. Within that, there is a subdirectory called GCC. This is where the main compiler code is. And within this directory, we have language directories. For example, we have something for C++, something for Java, etc. For C, the entire code is within this directory GCC itself. Source code language directory contains the parser, which is handwritten. Until 4.2, we had parser that was generated using Yark or Bison. Now, GCC has moved to a recursive descent parser. Parser creates a parse tree. That parse tree has to be converted to abstract syntax tree. Type checking has to be done, etc. So all that code is there. And then there is an interface to creation of generic. Generic is a collection of all kinds of parse tree nodes on different languages, and the GCC, rest of the GCC understands generic. From generic, GIMP representation is created. The backend specification is also in the same directory, but there is a subdirectory called config. So GCC/config, and within that we have, for example, i386. GCC/config/i386 is a directory where we have specifications for i386. And backends typically consists of 3 files, or maybe a 4th file also, which is kind of optional, but it's very useful. The 3 files are target.md. So for a given target, we will have the machine description file, we will have the header file, and we will have a C file. And then there is some description of the prototypes of the functions that we define in C file, because those definitions are required elsewhere in the GCC source, and therefore there is a target protos.h. So let's come to configuration and building. Given that this is the organization of the source code, let's see how do we actually configure GCC. So what do we mean by configuration? First of all, GCC, as we have observed, is a compiler generator, and it can generate compiler for many languages and many backends. It can be compiled on many many platforms. So we have to tell GCC, when we get the source code, we have to prepare the source code for our specific purpose. It's a general code. Okay, so we have to define the platform on which it will be compiled. I get a C source code, and I'm going to compile it on an i386 machine. I'm going to compile it on a Spark machine. So these are the kind of things that we have to specify. So having defined what is the platform on which I'm going to build a compiler, I have to specify the platform for which I have to build a compiler. Am I going to generate code for i386? Am I going to generate code for some other machine, maybe MIPS? I have to specify the platform on which the generated compiler will run. I'm building a compiler on this laptop. Am I going to execute the compiler on this? Maybe it generates code for my proprietary processor. Is the compiler going to run on the proprietary processor, or is it going to run on some other machine? Okay, where do I want the compiler to be installed? Where is the machine description to be found? Etc., etc. So such are the questions that need to be answered before we actually build a compiler out of GCC. Well, we would like to specify what kind of libraries are required, etc., etc. So this is the process of configuration. Configuration essentially says, I'm going to customize the given generic source to my particular need. Having customized the source, then we will actually build the compiler out of it. So there are many prerequisites for configuring and building GCC. We need a native C compiler. GCC is in C, and therefore in order to create a C compiler out of GCC, we need a C compiler. We need a native C compiler. This could be the C compiler that's given by your vendor of the processor, or this could be a C compiler that you created out of GCC earlier. Or it may be that you want to build a cross compiler, and we'll talk about that concept later. So there are many other prerequisites that we have. For example, we need GNU Bash, we need awk, make, tar, etc., etc. The list is here. Again, it's a matter of information, so I will not go over the entire list. These are the conventions that we will use. We'll denote a GCC source directory by $sourced. A build directory will be shown by this shell variable called build, and install directory will be denoted by install. The most important thing is that these 3 subdirectories have to be independent of each other. One should not be contained in the other. They all may be contained in the same top level directory, but one should not be a parent or a child of some other directory. And the reason of this is not very difficult to imagine. The reason is that GCC actually generates a lot of code, and therefore it's better to keep all of them independent. So when we build GCC, this is what we specify. We say cd build. So we downloaded the source, we have untarred the source in a directory sourced. Now we change the directory to the build directory, and then we configure. The configure script itself is in the source. So we have to give the path to the configure program by specifying source D, and we specify the options, and the configure output is a customized make file. It creates a make file. Vinny briefly talked about what a make file is. It creates a make file, and this make file runs in over 6,000 lines. So you can imagine that's not very easy to read this make file. Then we run make, and it's customary, it's useful to redirect the error output to a file and standard output to a file so that you can examine actually what is happening. And we will see a very nice use of doing this towards the end of the lecture. Having built, so this make command will actually build the compiler. Then we need to install the compiler, because in order to run the compiler, we need to put the executable somewhere, we need to put the library somewhere, we need to put the header files. You know, when you say in curly in angular brackets include something, those header files have to be found somewhere. So all that has to be prepared, and that's called the installation. So we just run make install. So there's another option called make check, whereby we can check, run the test suite. There are lots of programs in GCC test suite which are run on the generated compiler to check whether the compiler is correct, but here we are omitting that. So what are the steps in building GCC? We have to build all prerequisites. We have to install all these things. These are the things that do not come with GCC and sometimes are not available by default. It's important for you to look at these steps very carefully. Every time you build something, you have to run ld config. ld config is something that sets up the path for searching of executables. So therefore, you can actually get the executables in place. So when we do GCC, when we do configure GCC, what are we doing? So here is a configure script. Configure script reads some data. Configure script reads some data from certain files, and we're going to follow a certain convention in our pictures. You must have noticed it, but let me emphasize. All throughout, we're trying to follow a simple convention. Everything in rectangular boxes is an executable. Everything that is not in a box is some kind of a file or some kind of a data. Something that's in oval is a library. Okay, this is a convention that we try to follow throughout the slides, and you should be able to parse a picture based on this convention. So this is an executable. It's actually a shell script. Okay, so it's a shell script which reads these files. These files themselves may be shell scripts, but we are not going to execute them. In this case, of course, they are not shell scripts. So this file, these files are read. So there are lots of things about what can be guessed. So you do not necessarily have to give all the information. A lot of information is guessed by the configure script. Reading, after reading these files and after looking at the options that we supply, configure creates these three files, and importantly, it creates something called config.status. It's in a box, it's a rectangular box, so it's an executable, it's a shell script. This, when executed, this reads input from config.h.in. Everything that ends with a in is an input file that provides a template. So config.h is a header file that's created which contains information about the particular configuration, and you'll find that in the GCC source code we will have somewhere at lots of places include config.h. Similarly, makefile.in is a template from which a makefile is created and a config is created. Config.h is created. Makefile is again shown in a rectangular box. Of course, you could argue that program is make and makefile is not an executable, but here for simplicity, let's take makefile as an executable which we execute with the make command. This is the process of configuration. Configuration does this. Configuration essentially creates a makefile which is customized to the path, the target, the language directory, the processor, the host, etc. All these things, and then we have to give make command in order to compile GCC. Now we saw this, how when we download a software, what are the usual steps that we do? We download and untar the source, we change the directory to wherever we have untarred the source, and then we say /configure, we configure the software. Let's say I have downloaded Employer. So I will run /configure and then I'll say make and I'll say make install. This is what we will typically do with any piece of software. Yeah. I'm saying this is for usual steps for a software, not for GCC. For GCC, there's a different set of steps, and that's what I want to emphasize. I want to highlight the difference between using configuring and building GCC and some other piece of software. What is the exact step? We download an untar and we say cd build. Okay, and we run configure from the source. The blue things are the things that are different. Okay, and then we run and we do make install. And why? Because unlike any other software, GCC generates a lot of source code based on our specification. When I configure and run Employer, it doesn't generate C source code. Okay, GCC generates source code during build steps. So in order to understand this, let's define certain terminologies. Let's define something called a build system. Build system, yeah. Yes. So the reason is that because the source code is generated, we do not know which file will be overwritten and how it will happen, and therefore these have to be in a separate. That's exactly what I meant by saying that source and build and install directories have to be distinct. Okay. So what is a build system? A build system is a system on which we are going to build a compiler out of GCC. Let's denote it with BS. When we build a compiler, the generated compiler is going to run on a host system. So I may build a compiler on this laptop. I may want to run it on some other machine. That's the host system. And when I run it on some other machine, I may want to generate code for a third machine. That is called the target system. So BS for build system, HS for host system, and TS for target system. It's possible that all three of them are same. I just download the GCC source, untar it on this machine, build a compiler on this machine. I say that I'm going to build a compiler on this machine. The generated compiler has to run on this machine, and the generated compiler has to generate code for this machine. That's called a native build. Everything is same. It's possible that I might want to build a compiler on this. I may want to run the compiler on this, but I may want it to generate a code which I want to download on my cell phone. It's possible, right? So we have build and host system that are same, but we have a target system that's different. That's called a cross compiler. Okay? And when all three of them are different, it's called a Canadian cross. Okay? So let's now look at certain basic concepts in building. We adapt a T notation from the Aho Sethi Ulman book. What does this T notation indicate? So the left part says that this is the input language. The right part says that this is the output language. So it describes the processor. And this part says that this is a processor which has been implemented in this language, or it executes in this language. Okay, we will choose one of them depending upon our requirements, and this is the name of the translator. Okay, so we will use this picture to talk about building of GCC. Okay, all of us have come across this term called bootstrapping. Okay, the compiler is bootstrapped from specification. The question is, we are building a C compiler. It's compiled using a C compiler. So who wrote the first compiler? Did the chicken come first or did the egg come first? Some people have tried to settle this argument. I read somewhere in the newspaper 2 weeks ago, and somebody found that the reference to the word egg was found in 8th century and the reference to the word chicken was found in some other century. And so they tried to settle this argument by looking at history. But here we are in a different situation. So let's look at the bootstrapping process for GCC. In this case, we customize our notation in the following way. We say this is a language of our implementation. So in the first case, what do is, let's assume that we have a bare bone hardware, we have no facility on it, but the program the hardware can execute only the machine instruction. Now mapping from an assembly instruction to a machine instruction is one-to-one and usually very easy. Okay, so let's assume that I am smart enough to be able to write a translator that takes assembly program, okay, and generates machine program. I'm writing an assembler, but this assembler has been written in machine language. It's possible for us to visualize that. Input language is assembler. Implementation, now this is not execution language, but I have chosen to use this language to implement this translator, and the output language is machine language, right? So now we have an assembler ready. Earlier I had to write a program in machine language, but because I have an assembler, I can write a program in assembly language, right? So I can then visualize defining a very trimmed down version of C, minimal features, just some addition over assembly. I want to keep it simple so that I can write a translator for it easily. So I write a compiler where input is C and the output is machine language, but I don't write this translator in machine language. I write this translator in the assembly language. Why is it that I'm able to write this translator in machine language? Because I have before this written an assembler in machine language. So the advantage of writing an assembler in machine language is that it allows me to write programs in assembly language. Okay. Having done this, now I have a compiler for C0. What it means is now I can write programs in C0. It's easier to write programs in C0 than in assembly language. Then I can expect to design a language. I can enrich my language. I can say now I want to add more. Maybe I didn't have a floating point. I had just the integers. Maybe I didn't have characters. So I said, okay, let me enrich my language. I will add more data types. And now I'll write my compiler using language C0. My implementation language is C0. And why am I able to write this translator using C0? For the very simple reason that I had written C0 compiler using assembler. In such a way, a time will come when I will reach Cn, the current level of C, and I can write a compiler for that language in terms of a language which is just slightly lower version of that particular language. So I will end up getting a compiler for C. I started off with machine language. I didn't have any other facility with me. I have bootstrapped my compiler without using any external facility. Now on my hardware, now on my new processor, I have a C compiler. This is the conventional notion of bootstrapping. GCC uses the term bootstrapping in a very different way, and we need to understand that. So the GCC view of bootstrapping is something different. And why is it something different? The previous slide that we saw, the previous example that we saw was we wanted to bootstrap a compiler. We wanted to build a compiler for a language because the language changed. Because I had a Cn-1 language and I want to add a feature to Cn-1 to make it Cn. However, that need not always be the case. I may want to write a compiler not because my language has changed, but maybe because I have discovered a new algorithm of optimization. So language could remain same. I may want to build a new compiler because I have discovered a new optimization, or maybe I have discovered a bug in my compiler. So I need to fix that bug. I need to recompile my compiler. So the reason of building a compiler need not necessarily be change in a language, which is where the conventional bootstrapping view comes in. The motivation for change could be that we now have a better compiler, and maybe some bugs have been fixed. Okay, so in order to build a new version of GCC, so we'll assume that we have an older version of GCC, or we have a native C compiler. How did we get native C compiler? Maybe we did bootstrapping, as we saw just now. So let's take it as given that there exists a C compiler, and now we want to build a new compiler, which is the situation that we are in. we have C compilers on our machine. We're going to download a new version of GCC and we're going to build a compiler out of that particular source of GCC. Bootstrapping, the definition of bootstrapping in GCC says that we have to do a 3-stage build. Stage 1 is build a new compiler using the old compiler. Stage 2 is build another new compiler using compiler generated from stage 1. Stage 3 is build another new compiler using the compiler generated from stage 2. And the requirement is stage 2 and stage 3 builds must be identical compilers. This is the definition of GCC bootstrapping. How many of you did? How many of you understood it? Just one, maybe 2, 3. I didn't understand it when I read it because I don't think this really explains something. Let's get to the brass tacks. Let's get to the bottom of the matter. Let's see exactly what happens. Okay, so we will once again use T notation of a compiler. Let's take an example of a native build for i386. What does it mean? It means that my build system is i386, my host system is i386, and my target system is also i386. We've been given a GCC source, and we have a native compiler. Let's call it CC. And now here, yeah. Yes, it has to be. It was there in the list. It has to be there. It has to be C95 compliant compiler. Okay. So I have a native compiler CC, and because I want my host system to be i386, I take a compiler which runs on i386, takes C as the input program and generates i386 code. What dictates these choices? The fact that execution language is i386 comes from the fact that my build system is i386. The fact that the output language is i386 comes from the fact that my host system is i386. I'm going to compile GCC source and it has to run on i386. So therefore it has to be compiled with a compiler that generates i386 code. Right? And what dictates this choice? So I've given input language and I've given target processor. What dictates this as i386? Because I want my target system to be i386. So I fulfill all requirements, all requirements of the parameters for customization, for configuration and building. So this is a C compiler. I have GCC source, which is nothing but a C program. So this compiler can compile GCC source. So I feed GCC source to this compiler. And this compiler is going to create an executable. This compiler is going to, for any C program, is going to give me an executable. However, because the input to this C program is the specification of a compiler, output will be a compiled version of the compiler. Output will have to be a compiler. And what will be the input language of the compiler? The input language of the compiler would be C because we specified C as the input language. The output language of the compiler will be i386 because we specified i386 as the target processor. The execution language of this compiler will be i386 because it was compiled using i386, right? So now we have got this compiler. This is my stage 1 build. Okay, now I have a program that will run on an i386 machine. This is my stage 1 build, which happens to be a compiler. It can compile, and because it takes C program, it can compile any C program. And because it can compile any C program, in particular, it must be capable of compiling the GCC source itself. So let's feed GCC source to stage 1 build, right? When we get stage 1 build, this is also a compiler. Note that this is now a compiler called GCC, not CC. Now we have discarded this native C compiler. We don't need it. We want a compiler called GCC. Now we compile GCC source using this GCC. What will be the output?